Okay, moving on, we are going to now tackle negative exponents and the complete law of exponents. Up until now we've been kind of doing one step at a time to get to this point. So now we're going to tackle where exponents can be any integer, both positive or negative. All right, so in this lesson and the next, it's going to refer to several of the equations used in the previous lessons. So it'd probably be helpful if you have some way of referencing these equations quickly. For example, maybe put them all down on an index card. Now you might be saying, well, a lot of them are repetitious or repetitions of each other, but if you look at them closely, notice how the beginning of the definitions begin with positive numbers or positive integers, and then we've moved to whole numbers because now we're going to move to all integers, which means positive and negative. So there is an evolution happening here, and you need to see all of the equations as they evolve. So if you can write all of those down on a reference card or an index card, that would be really helpful. So once you've done that, go ahead and continue the video. All right. Let x and y be positive numbers throughout this lesson. Recall that we have the following three identities, and this is 6 through 8. So for all whole numbers, and again, this is all whole numbers from our previous lesson, x and y. Notice how x to the nth power times x to the nth power, we can add the exponents, because again, this is for all whole numbers, so that includes 0, which is from the previous lesson. So that is going to be called equation number 6. And equation 7 is the raising a power to a power, so x to the nth power raised to the nth power is just a multiplication of the exponents. And again, it could be 0 or any positive integer. And that is going to be equation 7. And then our last one is the product of two factors, x and y, raised to a power, is the same as if we raise each of those factors to the same power. All right, so be clear that we want equation 6 through 8 to remain true even when x and y are integers. So now we're going to be an integer. Remember, the definition is positive and negative, or positive numbers and their opposites. So we're going to make this evolve from whole numbers to the next and last step for our purposes, which is going to be integers. So before we can say that, we first have to decide, what does something like 3 to the negative 5, what should that mean? And we would say that as 3 raised to the power of negative 5, or but keep in mind, it is the opposite of 5. And the reason why we use opposite of 5, you'll see later on, is sometimes you can have the opposite of an opposite. And again, you should be only write down things that you do not know or summarize. You should not be writing these down word for word, or you're going to take too long taking your notes. So again, as you watch the video, just write down or summarize things that are being talked about. So as in lesson 4, where we introduced the concept of the 0th power of a number, the overriding idea here is that the negative power of a number should be defined in a way to ensure that equations 6 through 8 continue to hold when x and y are integers and not just whole numbers. So that's kind of just, again, giving some reasoning to why we're moving from positive integers to whole numbers to now all integers, including negatives. So you might likely say that 3 raised to a power of negative 5 should mean negative 3 raised to the 5th power. However, if that is what it meant, then that is what we would write. There is no other way to write negative 3 raised to the 5th power. It is negative 3 raised to the 5th power, so 3 to the negative fifth power is something different. So let's see if we can equate it to or use our equation number 6 to see what it should look like, or what should 3 raised to the negative 5 equal. So consider this. If x is a number, then what value of x would make the following true? So if I have 3 raised to the fifth power times some number, how am I going to make that equal 1? So what could I multiply 3 to the fifth power by to make it equal to 1? Well, we want to believe that the equation 6 is still correct even when m and n are integers, and therefore we should have this. So if 3 to the fifth power times the opposite of the exponent 5, 3 to the negative fifth power, then because the rule says that we add the integers, then we would be adding 5 and a negative 5, or 5 and the opposite of 5. And when we do that, we get to 0. So 3 to the 0th power, which is 1. So that kind of goes back up to here. 3 to the fifth power times some number is going to be equal to 1. Well, it would be the opposite of the exponent. So the opposite of 5 would be negative 5. But again, what does that say about the value of 3 to the negative fifth power? We see that this is going to work, that it is the opposite, but what does this mean? What is 3 to the negative fifth power? If I were to simplify that, what type of value does it have? So the answer is, if the value 3 to the negative fifth power must be a fraction, because 3 to the fifth power times 3 to the negative fifth power has to equal 1, then that means this value has to be the reciprocal of the first value. And if we just want to use regular numbers, you should be familiar with, if I want to multiply 5 by something to get 1, then I would multiply it by its reciprocal. So the same thing holds true here. If I have 3 to the fifth power, then what I'm doing is multiplying it by a fraction. So 3 to the negative fifth power has to be a fraction, so that I get 1. So then, would it not be reasonable to define 3 to the negative fifth power in general as 1 over 3 to the fifth power? Again, if we plug this in, then it would be this times the reciprocal of this, which would be 1 over itself. So that leads us to our definition. For any positive number x and for any positive integer n, we define x to the negative nth power is equal to 1 over x to the nth power. Now you might be saying, why do we say positive integer here? Well, just like I mentioned before, this does not mean negative n. This means the opposite of n. So this is still a positive integer. We're just taking the opposite of it, and this is still a positive integer. Note that this definition of a negative exponent says that x to the negative first power is just the reciprocal, 1 over x, of x. Okay? So we're going to have a problem with just calling this a negative exponent. That's why it says for any positive integer n. Because if we're just talking about negative exponents, then be x to the negative first power would be 1 over x of x. So in particular, x to the negative first power would make no sense if x was equal to 0. Because again, we can't have 1 over 0. So that's why this can't be a negative, or this can't be 0. This has to be for any positive number x. So x in this case still has to be a positive number, because again, if x was equal to 0, we can't have 1 over 0. It's undefined. So this explains why we still must restrict x to be a non-zero number at this time. So in our definition, for any positive number x, Basically, it's any non-zero number of x for right now. All right, so the definition has a following consequence. Well, for a positive x, if x raised to the opposite of b is equal to 1 over x raised to the power of b for all integers b. Okay, so this is going to be our equation number 9. Make sure you include that on your index card because we'll be referring back to this. So this contains more information than just the definition of a negative exponent. Again, this is not x to the negative b. This is actually x raised to the opposite of b. So make sure that you remember that this just doesn't mean it's going to be a negative number. And the reason will be stated right now. For example, if it implies, let's say that b is negative 3 in this equation. So let's say b is negative 3. Then in essence, what you have is the opposite of negative 3. Well, what is the opposite of negative 3? It's positive 3. So that means in this example, it would be 5 to the third power is equal to 1 over 5 to the negative third power. Remember, there's no negative sign here, but remember we said b is negative 3. So that's why it's really important not to get fixated that this means a negative number. It means the opposite of whatever b is. All right, so we're going to do a proof of equation 9. So we're going to prove why this works. And there's 3 possibilities. For all integers, if we're talking about all integers, that means b can be greater than 0, b can be 0, and b can be less than 0. So we're going to prove it for all integers up here. So let's start with the first one. If b is positive, then equation 9 is just the definition of b raised to the opposite, x raised to the opposite of b. And there is nothing to prove because we've already talked about the fact that if this is a positive, then this is what results because we already proved that from before. So for any b that is greater than 0, like 1, 2, 3, or 4, then this is true. There's nothing left to do. But what if b is 0? Well, then that means, again, the opposite of 0 is 0, so that doesn't change anything. And therefore, we have raised to a power of 0, which is 1. And both left and right sides of the equation are 1. So again, this works. And equation 9 is correct. So finally, let's let b be a negative number. Okay, so something less than 0. Then if b is a negative n for some positive integer n, again remember this is still a positive number, the minus sign here means that we're taking its opposite, then the left side of the equation is x raised to the negative power of b means the same as x, and then we're going to take the opposite of negative n. Because remember, b can be anything less than 0, which means it's going to be the opposite of n. So the opposite of the opposite, and when we take the opposite of the opposite, we go back to a positive. So x is raised to the nth power. So the right side of equation 9 is equal to this. Or so we talked about the left side, now the right side. If this is the equation or the expression on the right side, and we write this again as using the definition, then we can say this. X raised to the negative nth power is, by definition, 1 over x to the nth power. Well, now this makes this a complex fraction. And how do we deal with complex fractions? Well, this becomes 1 times the reciprocal. So we simplify a complex fraction by using invert and multiply. Because if I multiply this by the reciprocal, xn over 1, then that's essentially what I get here. Well, 1 times x to the nth power is x to the nth power, which is the exact same thing we got on the left side. So the left side is equal to the right side. X to the nth power is x to the nth power. So that means the entire proof is complete for every set of integer, positive, 0, or negative. So go ahead and highlight the definition on your lesson worksheet and make sure you copy this into your journal. And again, if you're keeping an index card, make sure you include equation number 9. So here it is, the definition. For any positive number x and any positive number n, we can define x raised to the opposite of nth power is the same as 1 over x to the n. Note that this definition of a negative exponent says that x to the negative first power is just the reciprocal 1 over x of x. So as a consequence of this definition, that means for all positive x and all integers b, we get x raised to the opposite of b is the same as 1 over x raised to the b. When you are done with this, go ahead and continue. All right, so it seems like a whole lot of talk about negative exponents. Why do we even care about negative exponents? Well, as it has been indicated in Lesson 4, the reason for this consideration is the fascination with identities 1 through 3. That is those initial equations that we came up with, which were valid only for positive integers. Remember, when we first created this, we were only talking about numbers greater than 0. All right? Well, these identities should be valid for all exponents. So again, both positive, 0, and negative exponents. And these are the identities, these are the starting point for consideration of all other exponents beyond positive integers. Now we're talking fractions or all rational numbers. So even without knowing the aspects of these identities, we can see the benefit of having negative exponents by looking at the complete expanded form of a decimal. For example, the complete expanded form of 328 and 5,403 10,000s is, and this is going to be a little on the small side, but 3 is 3 times 10 to the second power, because that's 100. 2 is 2 times 10 to the first power, because that's 2 times 10. 8 times 10 to the 0 power, because that equals 1, and we have 8 ones. And then notice what happens with the decimals. This is 5/10, because 10 to the negative first power is 1/10. And then 10 to the negative second power, or raised to the negative second power, is 1/100th. Notice how that corresponds. This is 400ths. And then we have no thousandths, so it's 0 times 1/1000th, and then 3 times 1/10,000th. So notice the transition, 10 to the second power, 10 to the first power, 10 to the 0 power, and then 10 to the negative 1, 10 to the negative 2, so on and so forth. Okay, so we do need negative exponents. By writing the place value of decimal digits in negative powers of 10, one gets a sense of the naturalness of the complete expanded form as the sum of the whole number multiples of descending powers of 10. So not only do we have ascending powers of 10, 10 squared, 10 to the third power, we have descending powers of 10. So as numbers get smaller and partitioned more and more, we have descending powers of 10. All right, so let's take a look at the exercises on your lesson worksheet. We're going to complete exercises 1 through 10 on your lesson worksheet. So let's do exercise 1 first before you begin. Exercise 1 says to verify the general statement, x to the negative b, or raised to the opposite of b, is equal to 1 over x to the power of b 4, let's say that x is going to be 3 and b is going to be -5. Well, this is what you should have, and again, you want to make sure that when you are verifying something, you want to talk about it by splitting up the two sides of the equation. So if b were positive, then we just have what the definition states. However, b is negative. Remember, b is a -5. So that means we have to write it in this instance. So 3 to the opposite of a -5, or the opposite of 5, equals 1 over 3 to the -5. All right, so the right side of the equation, we're going to take a look at the right side first. That is 1 over 3 to the -5 is the same as 1 over 1 over 3 to the 5th power. And again, simplifying our complex fraction means that we multiply it by the reciprocal. 1 times 3 to the 5th power, which is 3 to the 5th power. Now, since the left side is also 3 to the 5th power, both sides are equal. So if we take a look at the left side, well, the opposite of a -5 is +5. So therefore, this is equal to this. So we know that they are the same. All right. Well, before we go and do that, go ahead and do exercises 2 through 10. And once you have completed those, then go ahead and continue the video to check your answers. All right, so here are the exercises for 2, 3, and 4. Go ahead and pause the video and check your answers, and then continue to check the rest of them. All right, and here are the answers for exercises 5 through 10. Again, if there's any one of these that you don't understand, make sure you write a question, highlight it, and bring it to class. Okay, going back to your math journal, we now state our main objective. For any positive number x or y, and for all integers a and b, we're doing our last 3 equations. So, again, these will all sound the same, but the key component is the fact that we're talking about all integers. So that means positive and negative, that these are going to be true. Again, add that to your index card as well. We're also going to claim that these are true based on 10, 11, and 12. That x raised to the power of a over x raised to the power of b is the same as subtracting a minus b. And the same thing if we have a fractional number, x over y, raised to a power, then that is the same as x raised to the power of a over y raised to the power of a. And again, for all integers a and b, it doesn't matter whether it's positive, 0, or negative. All right, so the identities in 10 through 12 are now called the laws of exponents for integer exponents. Remember, integer meaning all numbers, positive, negative, and 0. We're not talking about fractions yet, so these are just whole numbers and their opposites. And they clearly generalize our equations 6 through 8. All right, so they are valid even when a and b are rational numbers, which is positive and negative fractions. But that fact, and the fact that they are true for all real numbers, is only going to be proved in college. So you have a while to wait before you do that. But as you can see, these laws of exponents are extremely powerful. So we're going to prove the laws of exponents in the next lesson. For now, we just want to make sure we use them effectively. So in the process, we'll get a glimpse of why they are worth learning. We will show that knowing equations 10 through 12 means also knowing 4 and 5 automatically. So going back to equations 4 and 5. Incidentally, the preceding sentence demonstrates why it's essential to learn to use symbols, because if you were to use equations 10 through 12 stated in terms of just using specific numbers, the preceding sentence would not even make sense. So let's look at the claim that we made. This is going to be equations 13 and 14. And you already have these written down. So let's take a look at identity 13. Such says much more than equation number 4. Here a and b can be integers rather than just positive integers, and moreover there is no requirement that a has to be greater than b. All right, so now a could be less than b, it doesn't matter. Similarly, unlike equation 5, the a in 14 is an integer rather than just a positive integer. So again, we're going to make these apply to all integers all integers for a and b, and not just positive integers. All right, so exercise 11 and 12. We're going to go ahead and complete that on your worksheet. And then go ahead and continue the video to see the answers. All right, so this is what you should have. Again, make sure you do not forget the step that this should be 2 minus 5. All right, and then what would that be if you simplified it even further? And the same thing here. This would be, in essence, 16 minus a negative 3, which ends up being the same 16 plus 3. All right, so let's do the proof of equation 13, and I put it back up here again so you know which one we're talking about. The one that says that a, or x raised to the power of a over x raised to the power of b is the same as subtracting the exponents. So in your math journal, let's go ahead and start out by writing the proof. So remember that this as a fraction can be written, even though it's a division, can be written as multiplication. So x raised to the power of a is the same as multiplying by 1 over x raised to the power of b. And this is known by the product formula of complex fractions, or you can call it invert and multiply. It's the same thing. Well, then the next step is to write this in another format, which is, by definition, 1 over x to the power of b is the same as 1, or x raised to the opposite of b, and that is by equation number 9. We're just going backwards. Instead of starting with a negative exponent and going to a fraction, we're starting with a fraction and writing it as a negative exponent. Well, if that's the case, then by our equation number 10, we can write this as an addition of the exponents. So this would be a plus the opposite of b, which is being shown right here. And then because of the definition of subtraction, a plus the opposite of b is the same thing as a minus b. Therefore, notice how we started with this expression and we have finished with this expression, which means that this is true. All right, so let's do exercise 13 on your worksheet. Go ahead and do that and then continue the video. All right, so the answer for exercise 13 is if y raised to the negative first power times any number a is the same as multiplying negative 1 times a, which gives you a negative a. All right, before you do exercise 14, let's take a look at the proof of equation 14, which was a fraction. A fraction raised to a power is the same as raising both the numerator and denominator by that same power. So in your math journal again, we'll step this out. Remember that x over y raised to a power is, again, writing this division problem as a multiplication problem. It means the same as x times 1 over y, and this whole thing is raised to the power. And again, that is by the product formula for complex fractions. Again, if this is 1 over y, we can write it by definition that this is y to the negative first power. Okay, by definition right here. Again, since this is a product, that we keep the parentheses and it's both being raised to a power of a. Well, from that, we can, if that's the case, then by definition using equation 12, again, we're kind of going backwards here. We're saying that by this definition, we can write it as x to the a times y to the a. So we're just going to raise each one to the a power. Again, negative 1a times a is a negative a by equation number 11, also from exercise 13, you just did that. And now we're going to put this back in its fraction form. So if y to the negative a power is the reciprocal of y to the a, and again, that is using equation 9. Then we end up with x to the a power over y to the a power, and that is what we have at the end here. So we started with the left side, and we used our definitions and equations to get to the right side. All right, go ahead and try exercise 14. Again, make sure you list the process step by step and justify each step by using equations and definitions that we've been working with. So it's going to look very similar to your proof of equation 14. So try it out and then continue the video and see what you came up with. All right, so if we have 7/5 raised to a power of negative 4, can we make it 7 raised to the negative 4 over 5 raised to the negative 4? So the first step is to write this as a product formula of a complex fraction. And the next step is to write 1/5 as a negative exponent, so 5 to the negative first, and that's by definition. Now we use our equation 12. Taking a product and applying a power to it. So that is 7 to the negative 4th times 5 to the negative 1st raised to the negative 4th power. Then we do some simplifying. 7 to the negative 4th, and because we have negative 1 times negative 4, that becomes a positive 4. And now we are going to write this as using our equation 9. If we have 5 to the 4th power, then the reciprocal of that would be 1 over 5 to the negative 4th power. Again, using this backwards, this is not a negative, this means take the opposite. So the opposite of 4 is negative 4, and it goes down on as a denominator of the fraction. And then by simplifying this by the product formula again, since this is multiplication, it is also a division problem, and we end up with what is on the right side of the equation. Okay? All right, so let's summarize what we have. First of all, this is a pretty complex lesson, so you will want to view and reread your notes and try to summarize what has happened in your own words. And then again, assuming equations 10 through 12 are true for integer exponents, allows us to see that equations 4 and 5 would also be true for integer exponents. And they are worth remembering because they are so useful and allow us to limit what we need to memorize. So even though you have a list of about 12 different equations, now we've boiled it down to the ones you really need to know are 10 through 12, and then by consequence you have 13 and 14, which are also true. All right, we'll see you in class.